In this series, we'll explore word embeddings in natural language processing. In machine learning, embeddings refer to the process of representing complex, high-dimensional data such as words, images, or audio as numerical vectors in a continuous, lower-dimensional vector space. Also, in natural language processing, embeddings refer to representing natural language used by humans as real-valued vectors that can be understood by machines. Word embeddings are numerical representations of words designed to capture their meanings and relationships in a continuous vector space. Each word is mapped to a dense vector where the distance and direction between vectors reflect semantic similarities. In this video, we'll explore the Neural Probabilistic Language Model, NPLM, an early concept in word embeddings. This video was produced in Korean and then translated into English. The audio was generated by AI, text-to-speech. In this video, we will briefly review the NPLM paper and analyze the neural architecture of NPLM in detail. The NPLM was introduced by Yoshua Bengio et al. In their 2003 paper titled A Neural Probabilistic Language Model. In this paper, the authors proposed a method to dramatically alleviate the curse of dimensionality by learning distributed representations of words, which allows each training sentence to inform the model about an exponential number of semantically neighboring sentences. The model learns simultaneously a distributed representation for each word along with the probability function for word sequences. The core of this paper is a distributed representation of words for encoding meaning. Nowadays, this is called word embedding. The concept of embedding appears to have been used in natural language processing for quite some time. However, since the paper was published, it has gained widespread popularity. Now let's look at what a distributed representation of words is. Let's say we have a sentence in our corpus, "The cat is walking in the bedroom." We want to represent each word in this sentence as a numerical vector. First, we build a vocabulary like this using our corpus. Each word in the vocabulary is assigned a unique index. Using these indices, we can represent this sentence as a word sequence like this. A word sequence is composed of a set of tokens. A token is the most fundamental data unit of a sentence. A sentence is a unit of meaning, while a word sequence is simply the linear order of words in a sentence. One-hot encoding provides a simple way to represent words as vectors, but it has some limitations. One major problem is the high dimensionality of the resulting vectors, especially when dealing with a large vocabulary. This causes the curse of dimensionality problem. Additionally, one-hot encoding fails to capture the semantic relationships between words, as it treats each word as completely independent of others. In a one-hot encoding vector space, the distance between each word is the same, the square root of 2, implying that there is no semantic relationship between words. This prevents language models from capturing the semantic nuances of language. To overcome these limitations, Yoshua Bengio et al. Proposed a more advanced vector representation. Nowadays, this is called word embedding. One-hot vectors are usually very sparse and high-dimensional. A word embedding is a way of representing a word as a dense, low-dimensional vector of real numbers. In this example, the word embedding size is 4. Even if the vocabulary size is large, this size can be set to small. This will help overcome the curse of dimensionality problem. The one-hot representation is an example of a local representation. A single unit is dedicated to representing one specific word, meaning that the information in the word is concentrated in that specific unit. It is easy to understand how information is represented, but it struggles to efficiently represent abstract or continuous variables. Moreover, the loss of a single unit can lead to the complete loss of the specific concept that the unit represents. Word embeddings, on the other hand, are a type of distributed representation of words that are designed to capture the meaning and relationships between words. Information in a word is distributed into multiple units, each of which participates in representing different concepts. These units can represent a vast number of concepts, even abstract ones. Each word is mapped to a point in an m-dimensional embedding vector space. In this space, words that are semantically and syntactically similar are located close to each other, and words that are dissimilar are located far apart from each other. Embedding vectors allow language models to capture the semantic nuances of a language. These values can be determined through learning from data. We will look at this in more detail later. Next, let's look at a statistical language model. A language model is a machine learning model that learns from large amounts of text data to predict or generate natural language. The language model can determine the probability of a word or sequence of words appearing by learning patterns, grammar, and context. A goal of statistical language modeling is to learn the joint probability function of sequences of words in a language. The joint probability of occurrence of a word sequence W1T in natural language can be expressed as follows. Here, W1T refers to a word sequence consisting of T tokens from 1 to T. This probability can be expressed as the product of the conditional probabilities of a specific token appearing after a sequence of tokens. Let's take this sentence as an example. The cat is walking in the bedroom. The probability of this sentence appearing in natural language is as follows. This is the probability that the will appear at the beginning of a sentence. And this is the probability that the word cat will follow given the word the. This is the probability that is will follow given the word sequence the and cat. If we multiply all these probabilities in this way, we can get this probability. The probability that this sentence appears in this corpus is 1/5. Now let's calculate the right-hand side. In this corpus, the probability that the appears at the beginning of a sentence is 3/5. and the conditional probability that cat follows the is 2/3. And the conditional probability that is comes after they and cat is 1. If we multiply all the probabilities in this way, we get 1/5, which is the same as on the left. However, this model has limitations. For example, if the word sequence, the cat is does not appear in the training corpus, this joint probability would be 0 or undefined. However, in reality, this probability may not be 0, as word sequences that do not appear in the training data may appear in real natural language. This is called the sparsity problem. Due to the creativity of language, the number of possible word sequences that can occur in natural language is infinite. Since the corpus size is finite, it becomes infeasible to train the model for all situations in a language, making it impossible to accurately model the language. To alleviate this problem, we can use the n-gram model. N-gram models tackle the sparsity problem by considering smaller contextual units instead of whole sequences, which allows for more manageable and efficient training on limited data. The n-gram model can approximate this joint probability as follows, where n is the number of grams. An n-gram is simply a sequence of n words. If n is 3, i.e., a trigram model, the left side can be written as follows. The probability that this word sequence appears in the training corpus can be approximately expressed as follows. Let's compute the conditional probability that dog was is followed by running in this corpus. Using a count-based approach, this probability can be written as follows. The number of cases where dog and was appear consecutively is 2. And the number of cases where dog, was, and running appear consecutively is 1. So this probability becomes a half. And since there is no word barking in this corpus, this probability is 0. Additionally, this probability is undefined because dog and has do not appear consecutively in this corpus. Next, let's calculate the conditional probability that each word in the vocabulary will appear after dog was. The results are as follows. Running and walking are more likely to appear. Statistical language models can use these probabilities to predict which word will follow a given sequence of words. If you input dog and was into this model, it will output running or walking. Next, let's examine the neural architecture of NPLM proposed by Yoshua Bengio et al. The goal of this model is to predict the next word given a sequence of words. A sequence of words is fed into the input layer. In this example, 4 grams are used. When our corpus is like this, and our vocabulary is like this, the index of the word the is 8, and the index of the word cat is 2. The target for this input is the word walking at index 9. The matrix C represents a set of word embedding vectors. The size of the matrix C is V by M, where V is the vocabulary size, and M is the embedding vector size. Each row vector is an embedding vector for each word. For example, the second row vector is the embedding vector for the word cat. When these three words are input into the input layer, the embedding vectors corresponding to these words are selected from the matrix C. This is the table lookup in C process. The selected embedding vectors are concatenated into a single vector. This is the vector x. Since we use 4 grams, the size of this vector is 3 mm. The vector x is input to the hidden layer. The number of hidden units is h, and the activation function is the hyperbolic tangent. The capital letter H is the connection weight matrix between x and the hidden layer. The size is n-1 m by h. The connection weight matrix between the hidden layer and the output layer is a matrix U of size h by v. The number of neurons in the output layer is v, which is the size of the vocabulary. And the activation function is softmax. These outputs are the conditional probabilities of each word in the vocabulary appearing given the input, i.e. the context. This network is trained to maximize the conditional probability that the word walking will appear. The elements of matrices U, H, and C are updated via backpropagation. Once training is complete, we can obtain word embedding vectors for each word. Optionally, direct or residual connections can be used between X and the output layer. The output of each layer can be expressed by the following formula. B and D are biases. When you feed a sequence of words to a trained network, the network predicts the next word. In this video, we looked at the architecture of NPLM. In the next video, we will implement a simple NPLM using Keras.